Hello dear student. So I want you to tell me which of these are optically active molecules. Take 5 seconds. Look carefully. Now most of the students, even the strong students, will look at these molecules and they will find 0 chiral centers and will take this molecule as optically inactive molecules with confidence. But let me tell you, my dear friends, these molecules may be optically active or may be optically inactive. Now we will quickly revise some basic things of optical isomerism. Compounds which have same molecular formula and same structural formula but have different optical activity is called as optical isomers. Now what is optical activity? Certain substances possess the property to rotate the plane polarized light. Such substances are called as optically active substance and the phenomenon is called as optical activity. Optical activity of any substance is determined by using an instrument called as the polarimeter. So you can see the image of polarimeter. By using this instrument, you can determine the optical activity of any organic compound. Now let's see the polarimeter experiment. Here we are using normal light, which is an electromagnetic wave which has oscillation in all the directions and it is perpendicular to the path of propagation of light. So here you can see the unpolarized light, that is the ordinary light, and then we are using a polarizer, that is Nicol prism. What Nicol prism will do, it will convert unpolarized light into the plane polarized light. Okay, so here you can see vectors in all the direction of light and here only one component of the light. Okay, now you will have a sample tube here. Now in this sample tube you will keep an organic compound here which you want to study. Now plane polarized light will pass from the sample tube containing organic compound and after that there will be an observer which will see the deflection in the plane polarized light. If the observer see no deflection, means the compound is optically inactive. If observer see there is a deflection, then compound is called as the optically active. It is a very simple experiment. Okay, here you can see if there is a deflection in the light, it is optically active. If again there is deflection, it is optically active. If no deflection, optically inactive. Based on the optical behavior towards plane polarized light, we can classify compounds into two categories, that is optically active compounds or optically inactive compounds. If the molecule rotates the plane polarized light in any direction, then it will be considered as optically active molecule. If the net rotation of the plane polarized light is 0, then it will be considered as optically inactive molecule. Okay, now when we are saying the molecule is rotated in any direction, now see properly. If the molecule is rotated in the clockwise direction, like in this direction, then the molecule is said to be dextrorotatory. It is written with small d or positive sign. If the plane polarized light is rotated in the anti-clockwise direction with angle alpha, then it is called as the leorotatory. It is written with small l or the negative sign. Please note that D and L form are the experimental observation that cannot be predicted by just looking at the structure of the molecule. Quickly revise some important terms in the optical isomerism which generally confuse the student. Okay, so number one is the optically active molecules. So they are also called as the chiral molecules or asymmetric molecules or also called as the dissymmetric molecules. Okay, so both asymmetric as well as the dissymmetric molecules are optically active and this is very important issue. Next, what is optically inactive molecules? They are called as the achiral molecules. Okay, next, the molecule having chiral center does not necessarily means the compound will be definitely optically active, that is the molecule will be definitely chiral molecules. So chiral center is different thing and chiral molecules is different thing. Okay, so they are not same and it is very important. If one compound will be D, then its mirror image will be L. Means if there is any compound which rotates light in the clockwise direction and is a dextrorotatory, if we take the mirror image of this particular molecule, it will definitely rotate the light in the anti-clockwise direction and will be leorotatory, and we can tell this without doing experiment. Okay, so this is very important. So to identify whether the molecule is optically active or not, we need polarimeter experiment. Scientists studied thousands of molecules. They found some were optically active and some were optically inactive. From lots of studies, they found ultimate cause or the truth behind the optical activity. Now, what is ultimate criteria to show optical activity? A compound which is non-superimposable to its mirror image is chiral. Okay, what does it mean? We will see in a few minutes. Okay, so what is the conclusion? Take any molecule, take its mirror image. Now check the compound and its mirror image. If the compound is superimposable to its mirror image, then the molecule is called as optically inactive and they are identical with each other. If the compound is non-superimposable to its mirror image, then molecule will be optically active and they are non-identical and different compounds. Now let's study what is superimposable and non-superimposable phenomena. If you take a glass and if you see its mirror image, now take this mirror image and keep over this particular object. You will see this particular thing. From this thing, can you tell that this contain two different things? One is the real object and second is the mirror image. Will you able to do that? No, you cannot tell from this particular image because both these things are exactly superimposed on each other. Okay, and such molecule which are superimposable are optically inactive. Clear? Now take this particular hand, take the mirror image. Now keep this over the real object. You will see this is a real object and this is the mirror image. Now are they exactly superimposed on each other? The answer is no. So such molecules are called as the non-superimposable molecules or the objects and they are always optically active. Okay, now let's take the third example, that is the spoon. See the mirror image. Now take the mirror image. This is the mirror image. Now superimposable both of them? Yes, they are superimposable and the molecule will be optically inactive. Okay, so superimposability is a three-dimensional phenomenon. If the molecule is superimposable on its mirror image, then it should look as it is one. I hope it is very clear to you.
Now dear student, we have two methods to identify the optical activity of the molecule. Number one, straightforward, you have to take the molecule and put in the polarimeter instrument. By using the instrument, you can check the optical activity. Second method, as we have just seen, take the molecule, take its mirror image, check whether it is superimposable or non-superimposable. If they are superimposable, molecule will be optically inactive, and if they are not superimposable, then molecule will be optically active. Now, so we have a variety of complex molecules, cyclic, multicyclic, spiro, many big molecules, complex molecules. So it is not feasible. So it is not easy to take the mirror image of that molecule and check whether they are superimposable or not. Okay, it is easy to check in the simple example like glass or any tetrahedral molecule or simple molecules. Okay, but in the complex molecules, it becomes very difficult to check the mirror image, to check the superimposable or whether it is not superimposable. So scientists faced many problems in doing that. Okay, so what scientists did, they studied a lot of molecules. They keep that molecule in the polarimeter instrument. They check whether the molecule was showing optical activity or not, and then they gave some conclusion from their observation, from their study. Okay, let's see that.
What is scientist observation? Asymmetry, that is absence of any symmetry, in the molecule is responsible for optical activity in such organic compounds. Now next task is how to check symmetry or asymmetry in the complex molecule. So scientists gave some symmetry elements. First one is called as the SN, that is alternative axis of symmetry, and second is the axis of symmetry. Alternative axis of symmetry is further classified as S1, S2, S3, S4 and so on. Now what we generally study, that is the plane of symmetry or the center of symmetry. Plane of symmetry and center of symmetry are not different things. They are the subparts of alternative axis of symmetry. That is, S1 is nothing but representing the POS and S2 is nothing but representing the COS. So POS and COS are the parts of alternating axis of symmetry. Okay, so please remember it, it's very important. Now next important part is the asymmetric and dissymmetric compounds. Both asymmetric and dissymmetric compounds are optically active molecules. Then what is the difference? So POS, COS, AAOS and AOS, all four symmetry elements will be absent in asymmetric compound and will be optically active. But in the dissymmetric compound, POS, COS and AOS will be absent, but AOS will be present, that is axis of symmetry will be present. Okay, so such molecules are called as dissymmetric compound but are still optically active, or if we can say it is optically active or chiral molecules. So what we can conclude from this particular point is AOS, optical activity, that is chirality, does not depend on presence or absence of the AOS, and this is very important. It will come as direct statement form. Look at an important part. Optical activity or chirality does not depend upon the presence or absence of the chiral center. We have compounds with 0 chiral center, 1 chiral center or more than 1 chiral centers. Okay, so we have 3 categories. Compound which has only 1 chiral center will always be optically active 100%. Okay, except tertiary amine because of the flipping, as you have studied this in the general organic chemistry. Now, compound which has 2 or more chiral centers may be optically active or may not be optically active. Now, on this part, optical inactivity is caused by the internal plane of symmetry, that is POS, COS. Okay, and such compound are called as the mesocompounds. Now, the compounds with 0 chiral center, will they be optically active or inactive? And this is very important segment where students generally have confusion. Example of these compounds are the allenes, spiranes, biphenyls, alkylidenes, cycloalkynes. They have no chiral center, but still there are few of compounds which may be optically active or may not be optically active. Now let's see optical active and inactive compounds. First case is optical active compounds having single chiral center. So as we have already studied, that is chiral center or stereo center or stereogenic center or asymmetric center are same thing, but they are very much different, or they are not related to the phenomenon so called as the chirality or chiral molecule or the optical activity. Okay, so here you can see only 1 chiral center, here 1, here 1, here 1, because hydrogen, deuterium, deuterium and alkyl group 4 different groups. Here you can see sulfur is there, which is sp3 hybridized, but here oxygen 16, oxygen 18 isotopes, so this will be treated as 2 different groups. This is third, so all 4 groups are different, so sulfur is chiral atom. So chiral is not only carbon, it may be nitrogen, it may be sulfur. Okay, so in this way you can see in all these examples only 1 chiral center is present, so all these molecules will be 100% optically active. Clear? This is our first case. Okay, now see the most important case that we want to study with the 0 chiral centers. This is the molecule having 0 chiral center, again 0 chiral center, 0 chiral center, 0 chiral center, again 0 chiral center. So whether they will be optically active or optically inactive, let's study in this particular lecture. So these are special cases. First one is the cumulene, then biphenyl and cycloalkylidenes. So let's study first cumulenes. Cumulenes are of 2 types, even cumulene and the odd cumulene. Even cumulene means the double bond are in the even numbers, and odd cumulanes means double bonds will be in the odd numbers. Here pi bonds will be 2, 4, 6, 8. Here pi bonds will be 1, 3, 5, 7. Okay, so these are even cumulanes, these are odd cumulanes. So here double bond continuous, this is cumulene. 2 double bond, that is pi bond are 2, so this is even cumulene. Pi bond 1, odd cumulene. Again pi bond 1, 2, 3, 4 even, 1, 2, 3 odd, 1, 2, 3, 4, 5, 6 even, 1, 2, 3, 4, 5, that is odd cumulene. So what we have studied, there are 2 types of cumulene, even and odd, and now let's see the orbital diagram of the even cumulanes. Okay, so this is an orbital diagram of even cumulene. Carbon number 1 is carbon number 2, this is carbon number 3. Now this is 1 pi bond, as you can see, and this is the second pi bond, and both pi bonds are perpendicular to each other. Okay, why is it so? And the reason for this is the carbon, central carbon is the sp hybridized, having 2 p orbitals. One is the pz direction or the py direction, and they are perpendicular to each other. Because of this, the terminal carbon, this hydrogen and the chlorine, will be in the plane of paper, but this carbon, the terminal valency A and B are perpendicular to the plane of paper. And if you look closely, these terminal valencies, that is HCl and A and B, are not in the same plane, correct? And because of that, geometrical isomerism will not be seen. If you have studied geometrical isomerism, then you can understand what I am trying to say. Okay, now even number of pi bonds. So in the even number of pi bonds, this A and B are in the horizontal plane, this double bond is in the vertical plane, again this double bond will be in the horizontal plane, and the D and E will be in the vertical plane. So this is in the horizontal, this is in the vertical, so AB and DE are not present in the same plane. Okay, and they have difference in the bond angle, that is the 90 degree. ABCD are not present in the same plane, so they cannot show geometrical isomerism. So here what we have to see, that is the optical isomerism. Okay, this is the terminal valencies. You can see here there is a difference in the 90 degree angle. Okay, you can see the structure of even cumulene. This is the pi bond, this is the perpendicular pi bond, these are the valencies which are perpendicular. More you can visualize, you can understand the thing, more your mind gets clarity how the things are there. Now look at the pi bond. Now if the pi bonds are odd, then it is called as the odd cumulenes. So here 1 2 3 odd pi bonds, so this is odd cumulene. So look at here, this A and B in the vertical plane, double bond in the horizontal, again double bond in the vertical, double bond in the horizontal, and D and E are present in the vertical plane. So the terminal valencies are vertical means the bond angle is 0 degree and they are present in the same plane, and you can clearly visualize the things here. This A and B and C and D, can you see they are lying in the same plane of paper? So ABCD, all four atoms ABCD are present in the same plane. So in this situation the molecule can show GI but cannot show optical isomerism, and it is very important. You have to correlate two things simultaneously, that is the geometrical isomerism as well as optical isomerism, and it is very important for JEE Advanced. Okay, here now see the 3D molecular diagram. See the 3D diagram for the odd cumulenes. See the terminal valencies. This is suppose horizontal, this is vertical, this is horizontal, this is vertical, and again this is horizontal. So horizontal, they are lying in the same plane. I hope it is very clear. So cumulenes with even number of pi bonds cannot show geometrical isomerism but can show optical isomerism. But with the odd number of pi bonds, it will show geometrical but cannot show optical isomerism. And this is the conclusion.
Okay, now let's see. This is the physical model of the even cumulene system. This is the first double bond and this is the second double bond. These are the two valencies of this particular carbon and these are the two valencies of this particular carbon. Okay, so now look here very carefully. The two and this two, that is the four terminal valencies, are not in the same plane. Okay, so these two and these two are perpendicular to each other. So when you cut this molecule in this way, here is one part and here is one part. Okay, that means you can check here plane of symmetry, correct? So if there is a plane of symmetry in this particular molecule, molecule will be optically inactive, and if there is no plane of symmetry, molecule will be optically active. And second point is why this molecule don't show geometrical isomerism. Look carefully, distance from this particular part to this particular part, suppose this is L1, and if I interchange this red and green atom here, then again distance from here and here is again L1. That means distance from this and this to this side is same. So on interchanging, there is no length change. Okay, so this molecule will never show geometrical isomerism. So in this case, you have to check whether it is optically active or optically inactive. So to check this, you have to check the plane of symmetry. Now you can have two plane, one cut, slice cut in this way. So this and this, if they are same, then there will be a plane of symmetry. If you cut in this way, then this and this, if they are same, then there will be a plane of symmetry. And if the plane of symmetry is present, then the molecule will be optically inactive. Okay, so this is a 3D representation. I hope it is very clear to you. Okay, look at this system. This is the odd cumulene system, and Here you can see the terminal valencies here are in the same plane, as you can see. Clear? So in this system, this molecule will be capable of showing geometrical isomerism, and this will not show optical isomerism because the molecular plane, that is plane of symmetry in the molecular plane, this will always be there whether the molecule will be identical or not. Okay.
Now, how to remember this particular thing without confusion? Remember the word God. See OD. OD means odd number of pi bond, that is 3, 5, 7, 9, etc. Odd number of pi bonds will definitely show geometrical isomerism, but even number of pi bond will not show geometrical isomerism but can show optical isomerism. Okay, now see some examples on the basis of the cumulenes. Before going to solve examples, you should have prior knowledge of the geometrical isomerism, how to identify geometrical isomerism, what are the situations or the cases which show the geometrical isomerism, as well as you should be able to see the plane of symmetry, center of symmetry, etc. Okay, then and then only you can be able to solve these particular questions. Now let's see first example, ethene, CH2, CH2 double bond. So odd number of pi bond, only one pi bond is present, so terminal valencies are in the same plane. If they are in the same plane, they will show geometrical isomerism and not optical isomerism. So this compound will be 100% optically inactive. Got it? It's a very important point. Now let's see this, the orbital diagram, the pi bond perpendicular, all 4 hydrogen in the plane of paper, as you can see the different orientations. And as I said, if you remember geometrical isomerism, here you have to check geometrical isomerism. So here C double bond C, H H H H. So this A is equal to B, that is hydrogen hydrogen, equal H is same as H, that is C is equal to D. So this will not show geometrical isomerism. So this compound will be optically inactive as well as it will not show geometrical isomerism. And this way simultaneously you have to deal with optical isomerism and the geometrical isomerism. Next example is the 1,2-propadiene. So here you can see this particular molecule, C double bond C, H H H H. So definitely here you can see number of pi bonds are 2 here. Okay, and if there are even number of pi bond, you have to check optical isomerism and not geometrical isomerism. Okay, so if you check the optical isomerism, now you have to check the symmetry, that is POS, COS, and here you can see the plane of symmetry is present. Okay, so this molecule is the optically inactive molecule and number of plane of symmetries are the 2. Now see the orbital diagram here for better understanding. Pause the video and you can see the molecule. Okay, and try to check the POS or the COS. Next example is the 1,2,3 butatriene. So number of double bond are the 3. 3 means odd, odd means God, that is will show geometrical isomerism and will not show optical isomerism. So this compound, number one thing, will be 100% optically inactive. Now it can show geometrical, so let's check the geometrical conditions. So here restriction in the rotation, here all 4 valencies are the same, that is A is equal to B, C is equal to D, so it will not show geometrical isomerism as well. Okay, and you can see different orbital diagrams for better understanding. Pause the video and understand the geometry of the molecule. Okay, now dear student, we just have completed the cumulenes, that is even and the odd cumulenes. But I would like to ask you a simple question. What if instead of continuous double bond we had continuous rings? So what will happen? So let's see. If in place of double bond I put a ring, then these compounds are called as the spiro compounds, and this thing, as the number of ring are even, so this is called as the even spiro. Next, in place of 3 pi bond I can place 3 rings. Again, when we have 3 pi bonds we called it as a old, that is odd cumulenes, sorry. And in case of 3 rings we can say this, as this is 3 is the odd number, so we can see is the odd spiro system or the odd spiro system. Okay, the central carbon here have hybridization sp, which is linear geometry, but here the central carbon is sp3 hybridized, And sp3 hybridise is a tetrahedral geometry, a very specific geometry, where the bond angle between the four groups is 109 degree approximation. Okay, and because of this sp3 hybridization, the spiro, they will try to be at perpendicular position with each other. Okay, and that is what we have to see. So here you can see, first of all, the 2D representation of this compound, and all compounds have continuous rings, maybe 4 carbon, 5 carbon or 6 carbon. Okay, so all these compounds are called as the polyspiro compounds or the spiro compounds. Okay, in reality they don't exist like this, they exist as like this. These two rings are perpendicular with each other. Why? Because this central carbon is the sp3 hybridized, and bond angle in all the four bonds will be equal to 109 degrees. Okay, now because of this, the two terminal valency of this ring will be in the plane of paper, but the other ring will not be in the plane of paper. So terminal valencies of both the ring are perpendicular, that is bond angle between them is 90 degree. Okay, so what is the conclusion? Terminal valencies of the even number of ring lies in different plane, same as what we have seen in the double bond. Okay, again here two rings exist as the perpendicular, so actual molecule will be like this. So terminal valencies, as you can see, there's 90 degree difference in the angle, so they will be in the different plane. 3 odd, so here terminal valency in the same plane, here odd, terminal valency in the same plane. So what is the conclusion out here? Polyspiro compounds with even number of ring, polyspiro compound with odd number of ring. So here rings n is equal to 2, that is even, n is equal to 2, again even, here n is equal to 3, odd. So rings here 2, 4, 6, so even in numbers. So all four terminals valencies are not in the same plane in such conditions. So here you have to check for the optical isomerism and not geometrical isomerism. So this compound will never show geometrical isomerism but can show optical isomerism. But you have to check for the number of plane of symmetry or the center of symmetry. If the plane of symmetry or center of symmetry is present, then the compound will be optically inactive, but if they are absent, the compound will be optically active, even without having the chiral center. Just same as what we have seen in the Cumulenes system. Okay, here n is equal to 3, number of rings 3, that is odd, so it may be 3, 5, 7, anything odd number. So in this case all four valencies which are on the terminals will be lying in the same plane. So in this case you have to check for the geometrical isomerism and not for the optical isomerism. So these compounds will be 100% optically inactive, but may show geometrical isomerism or may not show geometrical isomerism depending on the condition.
Start now. Now dear student, if we replace double bond with the ring, this is a Spiranes system. Okay, so if you can see properly here, this is the first ring and this is the second ring. So in the 2D representation, we feel that both the rings are in the same plane, but in reality you can see here one ring is exactly perpendicular to the second ring. Clear? So if we attach two valencies here at this terminal and two valencies at this particular terminal, now look carefully, these two valencies terminal of this carbon and these two valencies of this carbon are not in the same plane, they are perpendicular. So here in this case, when the rings are even, you will definitely not going to see geometrical isomerism. In this case you have to check whether it is the optically active or inactive molecule. Now I hope it is very clear to you. Again here one important point you can see here, that is this particular central carbon, the joining atom between the two rings, okay, the midpoint, this is sp3 hybridized. So this is proper, you can see a tetrahedral geometry here. Okay, like I will show you the reason why the two rings are perpendicular to each other, because of the sp3 hybridization of the central atom. So this is the central atom, and now you can clearly see the proper geometry with 109 degree angle. Clear? I hope it is very clear to you.
Now let's solve some questions here. Identify types of isomerism shown by following compounds. So here this is a polyspiro system. Now first of all count the number of rings. So n will be equal to 1, 2, 3, 4, 5, 6. So n be equal to 6. So 6 means this is even in number. Okay, now if these are even, that means terminal valencies are in the same plane or not in the same plane. Will not be in the same plane. So here what we have to check, optical or geometrical? We have to check here the optical isomerism and not geometrical isomerism. Okay, now if you carefully see, there is no plane of symmetry present, there is no center of symmetry present. Okay, the molecule will be optically active. Clear? Solve the second question. Here number of ring will be 3, that is odd. If they are odd, then what we have to check, terminal valencies will be in the same plane or the different plane? Will be in the same plane. Now check, that is geometrical isomerism or optical isomerism. Geometrical isomerism. Optical isomerism will not be present here. Okay, so if you check the geometrical isomerism, terminal valencies, look at here, they are not same. A is not equal to B and C is not equal to D, means geometrical isomerism is present here. Okay, now let's solve question number 3. Take your time. Okay, if you have solved, let's check here. So here number of rings will be 3, that is odd in number. So what the trick we have, that is the God. If number of rings or number of double bond or number of double bond plus ring, if the value is odd, then they will show geometrical and not optical. So this compound will never show optical isomerism but can show geometrical isomerism. Now check the condition for geometrical, that is iodine and hydrogen not equal, chlorine hydrogen not equal. So this compound will be showing geometrical isomerism and will be optically inactive. So simultaneously in such complex system you have to check geometrical as well as the optical activity. Now let's take the next case, that is cycloalkylidene. What we have done in this case is that one of the double bond in the allene is replaced by one cycloalkane ring. Means if this is the system, then we have changed this double bond with this particular ring and this double bond is at stage, you can see. So such a system having ring plus pi bond is called as cycloalkylidene system. So whenever there is continuous pi bond, the system is called as the cumulene. When there is continuous rings, then the system is called as the pyrene system or the polyspirene system. And when there is a ring plus pi bond, the system is called as cycloalkylidene system. Okay, now here let's see, if the number of double bond plus ring, if it is even, then terminal valencies are again perpendicular to each other and will show optical isomerism just like previous cases. And if the number of double bond plus ring is odd, that is 3, 5, 7 etc., then terminal valencies will lie in the same plane and here you have to check for the geometrical isomerism. Okay, so you can again use the trick, that is the God. If the number is odd, check geometric, and if the number is even, check optical isomerism. I hope it is now very clear to you. Okay, at the end of this particular lecture we will summarize and we will see under one slide, and by using that single page you will be able to solve all types of questions. Okay, now please see some visualization of the cycloalkylidene system and then we will solve the questions on the basis of this particular system. So here there is ring, double bond and CH2. So see the visualization. Pause the video and try to see what is the geometry of this particular molecule. Now see the geometry of the second question. Here by replacing one hydrogen they have attached OH group. Okay, and here by replacing one hydrogen they have added COOH group. Now see what is the geometry here. This is the COOH group, this is the H, this double bond, this is OH. So if you rotate the molecule, see this angle, see the image and the diagrams from all the angles, all the sides out here. Please see. Next see the third molecule. Now they have added 2 double bond and central ring. So system is n is equal to 3, that is odd because double bond will be equal to 2 plus ring will be equal to 1. So 2 plus 3, that is the odd system. See the diagrams, so you can clearly understand the geometry of this particular molecule. Solve the following questions. Identify following compounds which show geometrical or optical isomerism. So there is ring plus double bond. So double bond plus ring will be equal to 2. So 2 is the even number. So God is our trick. If the number is odd, then check geometrical. If the number is even, then check optical. So check optical isomerism, then check the POS here. If POS is present, yes, here if you have studied the POS, you can see the POS is present, then the molecule will be optically inactive or optically achiral in nature. Okay, and as you can see, geometrical isomerism will be definitely absent here. Okay, next, if the double bond plus ring again 2, that is even, then check what we have to check, optical isomerism. POS is present, yes, POS is present, and again the molecule will be optically inactive. Okay, or the molecule is achiral in nature. Clear? Now check the molecule number 3rd. Double bond plus ring will be equal to 1 and 2. Okay, so again this is even, so what we have to check, optical isomerism. If we check the optical isomerism, then if you can see the plane of symmetry or center of symmetry, they will be absent here. If both will be absent, molecule will be optically active or the chiral in nature. Clear? So this is very important. Now check the next case. Here double bond plus ring, system will be equal to 2. Okay, again even in number. Then check the optical isomerism. Now to check this, first of all see the COS or the POS. Yes, POS is present here, and if the POS is present, molecule is be optically inactive or the achiral in nature. Okay, and the last molecule check, double bond plus ring, again will be equal to 2. Okay, this is even, molecule will be optically active or maybe optically inactive. Let's check optically active inactive on the basis of POS. Again POS will be absent, molecule will be optically active. Okay, so this is very important. If I would like to add one extra thing here, let's check this particular molecule. Don't check geometrical isomerism on this 2 system, but you can check geometrical isomerism on this only one system. So if you see geometrical isomerism on this one system, you can see, so this is restricted rotated system, so this is CH3Cl which is not equal, and this part and this part is different. That means on this particular segment, this molecule is showing geometrical isomerism, but on this whole system, if we consider restricted rotated system as double bond plus ring, then it will never show geometrical isomerism at this particular segment. And this is very important questions out of here. Okay, so it is very complex. You have to be very clear with the geometric, very clear with the optical, and then you have to apply, you have to solve the questions, complex question, then you will be able to solve this particular questions. Okay, again, geometrical isomerism absent which system and this system. If you consider this as the RRS, geometrical isomerism will be absent. But if you see the hidden RRS system, geometrical isomerism, this is sp3 carbon, this is sp3 carbon, so geometrical isomerism is present in this system on this particular RRS. Okay, so this is hidden RRS. Clear? Okay, so the last part is the Atropisomers, the stereoisomers which are arised because of the restriction in the rotation about the single bond because of the steric repulsion. These are of 2 types, biphenyls and the terphenyls. Let's see in detail one by one. So here in the biphenyl system, as you can see, the rotation is possible around the single bond and it takes place at the room temperature. So the both ring are not coplanar and they will convert into each other. So here by rotation about this bond, this will convert into this, again by rotation in this bond, this will convert back into this particular point. Okay, so here rotation about carbon-carbon single bond is possible. Okay, and POS is present, molecule is optically inactive. Clear? But in this case here, if you have a bulky group at this position, then there will be high steric hindrance. Okay, and because of high steric repulsion, the potential energy of system increases, stability will decrease, and when this bond will rotate, you will get this system. Now in this system you can see steric repulsion is reduced, potential is reduced, stability is increased. So this molecule will try to remain in this particular system and will not go in this system. Okay, so rotation about single bond is restricted here, right? Now this is the molecule which exists as equilibrium in this form. Okay, now please see 3D diagrams here, all the side view, front view, so that you can understand the geometry here. Okay, and once you understand the geometry, you can visualize the thing and it will help you in the solving the questions out there. Clear? Now look here, this is the biphenyl. Now we have replaced the hydrogen with the 4 bulky groups, that is CH3, CH3, NO2, NO2. Okay, now this will rotate because here is a huge steric hindrance will be there and it will exist in this particular form. Now look 3D diagram of this molecule. See, the two rings are perpendicular to each other. Okay, one CH3 is here, one CH3 is here, one NO2 is front side, one NO2 is in the back side. Okay, so to reduce the steric hindrance, they are perpendicular to each other. Clear? See this view as well. Look all the 4 views. So you will get the idea of geometry, so it will help you in identifying the POS or the COS from the system. Okay, now if the 3 rings are present, the system is called as the terphenyl system. Now out of these 3 rings, 2 rings will be in the same plane and 1 ring will be in the opposite plane. Okay, so this molecule will look like this. See, because the Me and ethyl are the bulky group here, so there is a steric hindrance. This is the bulky group, steric hindrance, bulky group, steric hindrance, bulky group, steric hindrance. So this will rotate, this will rotate, this and this ring will be perpendicular, this and this ring will be perpendicular, but this and this ring are in the same plane. Clear? And you can see this in this image. Look, this ring in the same plane, but they are perpendicular with the second ring. Okay, see the view properly. So to reduce the steric hindrance, they have adjusted themselves in such a way that there will be minimum steric hindrance. See the last view as well. So let's see the conclusion. In the atropisomers, we have 2 types of system, biphenyl and the terphenyl system. You have to identify the system first of all. If there are bulky groups present at these positions, then both ring will be in the perpendicular position and will never show geometrical isomerism. So you have to check the optical isomerism here. If the molecule is having COS or POS, then it will be optically inactive, but if they don't have, then it will be optically active. In case of terphenyl, 2 rings, terminal rings, lie in the same plane. So you have to check here optical isomerism or geometrical. Yes, so you have to check here geometrical isomerism and not optical isomerism.
This is the biphenyl system. That means 2 rings are here and this is the central connecting bond between this carbon. Now here it can freely rotate around this carbon atom. Okay, so rotation is possible at this particular carbon because this is carbon-carbon single bond. Okay, so these 2 rings can be perpendicular to each other, they can be parallel. Clear? Now if we attach 2 bulky groups here, like at this position, let's see. See, now we have attached 2 bulky groups here and 2 here, and because of the repulsion, this is a static repulsion here, this steric repulsion here, sorry, and because of this repulsion, to minimize the repulsion, this ring rotates in this way and now it will attain this particular geometry. Clear? Now you can clearly see that one ring is perpendicular with the other ring. Okay, so in this case you have to check optical isomerism and not geometrical isomerism, and so you have to cut this particular thing. This is the plane of symmetry and this is the plane. If there is a plane of symmetry, this molecule will be optically inactive, and if there is no plane of symmetry, molecule will show optical activity. But never check geometrical isomerism in this particular system. This is the biphenyl system. If we attach one more ring here, that ring will be again like this. Yeah, the parallel with the terminal ring, and that will be terphenyl system. And in the terphenyl system, you have to check geometrical isomerism. Clear? Now, I hope with this model, this is helpful for your understanding. Clear? Okay.
Now let's solve some example on this part. So in the first question, which system is given? Biphenyl system. Okay. So what we have to check here? Optical isomerism. And in terphenyl, what we are checking? Geometrical isomerism. Clear? So check here optical isomers. Now check POS is present or absent? Yes, POS is absent here. If POS is absent, substance will be optically active. So this molecule will be optically active or not? Yes, it will be optically active, or we can say it's a chiral molecule. Clear? Next, see. Again, this is a biphenyl system. So what we have to check? Optical isomerism. POS is present or absent? Yes, POS is absent here. And if it is absent, the molecule will be optically active and it may be called as the chiral molecule. So in this way, you have to solve the question. Okay. Now let's solve the next question. Now which system is given? Terphenyl system. 3 rings are given. So in terphenyl, always check geometrical, not optical. Now to check geometrical, you have to consider this particular part as the restricted rotating system. This is called as the A, B, this is C, D. Will not be equal, will not be equal. So this will be showing geometrical isomerism. Okay, it is very, very important. Now solve the next question. Again, terphenyl system, check GI, not OI. Now if we consider this part as the restricted rotating system, this will be AB not equal, CD equal. So if C and D are equal, then it will never show geometrical isomerism. Okay. Now if they give you some more complex question, let's see here. This is the RRS. First of all, this terphenyl system, check GI. Now here C and D not equal, but here what they have given? Initially they have given methyl methyl and BRH. So first check these two parts, methyl methyl. If they are same, then move ahead. Again here Br and H means they are different, so A not equal to B. So in this case also GI will be seen. Clear? So here properly you have to check the situation, apply the rules, and then you can be able to solve the questions out there.
So dear student, I hope you have enjoyed this particular lecture. So what you have to remember in this particular complex question is this: you have to count number of double bond. If molecule have number of rings, then count the number of rings. If molecule contain double bond plus rings, then count the number of double bond plus rings. And if the count is even, then you have to simply check and go for the optical isomerism. Okay, then you have to check the POS, and if that is present, then optically inactive, and if not, then optically active. But when the count is odd, then molecule will never show optical isomerism. You have to go for the geometrical isomerism. Next, in the terphenyl and the biphenyl system, you have to look for the optical isomerism, and in the terphenyl you have to look for the geometrical isomerism, as the terminal valences are in the same plane. Now, apart from that, you have to remember one important thing is that now in the even number of system, that is the double bond or the ring plus double bond, if that is even, as we are saying that do not check geometrical isomerism, but you have to check any restricted rotation side. If it is there, hidden side, and if it is showing the geometrical isomerism, you have to check that particular thing. Okay, so this is very, very important. Clear? So for geometrical isomerism, you have to be very much careful about any single side which can show geometrical, then you have to take the geometrical isomerism. I hope it is very, very clear to you. And the questions that we have seen in the initial slide, then now you will be able to solve all those questions. Okay, I hope you have enjoyed your lecture. Thank you so much.